Hello again. Today we'll continue our discussion about the Internet of Things architecture part 2. I already uploaded the slides and the name of the file is Internet of Things architecture part 2. So today we will focus on functional concepts for implementing the Internet of Things. In today's rapidly evolving technological scape, the Internet of Things is transforming how we interact with the world around us. But what are the fundamental building blocks that make this interconnected world possible? Let's explore the key enablers of Internet of Things. At the heart of any Internet of Things systems are sensors. These are devices act as the eyes and ears of the Internet of Things, gathering data from the physical environment. They measure everything from temperature and sensor to motion and light. The real advantage, they provide real-time insights into physical conditions, enabling us to monitor and react to changes instantly. Next, we have connectivity. This is the lifeline of the Internet of Things, enabling devices to communicate with each other and with the cloud. Whether it's through Wi-Fi, Bluetooth, cellular networks like 5G or 4G, or low power wide area networks. Robust connectivity allows for seamless data transmission, enabling remote monitoring and control of devices from anywhere in the world. Finally, we have cloud computing. As Internet of Things devices generate vast amount of data, the cloud provides the essential infrastructure for storing, processing, and analyzing this information. The cloud's scalability, flexibility, and accessibility empowers us to make data-driven decisions, unlocking the true potential of Internet of Things. So, sensors, connectivity, and cloud computing are the pillars that support the Internet of Things. Together, they can create a powerful ecosystem that's transforming industries and improving lives. Continuing with Internet of Things enablers, we have edge computing. Edge computing brings data processing closer to the source, right where the data is generated. This reduces latency and bandwidth usage, leading to faster response time. Imagine a self-driving car making a split-second decision based on real-time data. That's the power of edge computing. It also enhances data security by processing sensitive information locally. Next, we have AI and machine learning. AI and machine learning are the brains behind the intelligent Internet of Things systems. Those technologies analyze vast amounts of data, identify patterns, and make predictions. This leads to predictive maintenance, optimized processes, and personalized user experiences. Think of a smart home that learns your habits and adjusts settings automatically. Finally, we must address security. Security is the paramount in the Internet of Things landscape. Protecting devices and data from cyber threats is critical to ensure data integrity, safeguard user privacy, and maintain system reliability in an interconnected world. Robust security is not an option, but a necessity. So, edge computing, AI, machine learning, and security, these are the pillars, again, in addition to what we have discussed in the previous slide, that enable a robust and intelligent Internet of Things. So I just wanted to talk about these pillars again because we have introduced them before. Enablers. We have introduced them before in a previous lecture, but I just wanted these two slides to summarize what we have discussed before. Now, imagine a world where computers filled entire rooms, requiring specialized technicians and consuming a vast amount of power. It's hard to believe, but this was the reality of computing not so long ago. Today, we carry powerful computers in our buckets, on our wrists, and even embedded in our clothing. How did we get here? So let's explore enablers that made this transformation possible. The key to portability lies in miniaturization of a hardware. Over time, advancements in technology allowed us to shrink the size of electronic components dramatically. This This shift from bulky vacuum tubes and transistors to integrated circuits and microchips enabled the creation of smaller and more efficient devices. The result, the transition from room-sized computers to the portable devices we use today. The miniaturization has led to increased accessibility and flexibility for users across various applications. We can now access information, communicate, and work from virtually anywhere. Portable devices have empowered us with more have empowered us to be more productive, more connected, and more mobile than ever before. So, portability has revolutionized the way we live and work. It has transformed computing from a specialized tool for experts to an integral part of our daily lives. In this slide, I want you to look at these processors. Notice the dramatic reduction in size. This miniaturization of processors has been the driving force behind the development of personal mobile devices. Imagine trying to fit a desktop computer's processor into your smartphone. It simply won't be possible. This miniaturization has led to increased portability, energy efficiency, and performance in smaller devices. We can now carry powerful computers in our pockets, on our wrists, and even embedded in our clothing. This has transformed how we work, communicate, and interact with the world around us. The ability to pack more processing power into smaller spaces have fueled the mobile revolution, enabling us to access information, entertainment, and communication on the go. So, in today's world of interconnected devices and constant connectivity, power efficiency is paramount. But how do we achieve this? Let's explore the critical enablers of low power and low heat. To understand this concept, we need to delve into technologies that make it possible. First, we have low power architecture, such as ARM processors. These processors are designed to perform tasks efficiently, minimizing energy consumption. Think of it as a highly efficient engine that uses less fuel to travel at the same distance. Next, we have low power radios like Bluetooth low energy. These radios um, uh, um, uh, are designed for short range communication with minimal power consumption, making them ideal for devices like wearable and Internet of Things sensors. Next, sleep mode. Sleep modes are another crucial enablers. Devices can enter a low power state when not actively in use, conserving energy. For example, Internet of Things devices can enter sleep mode and wake up only when needed to collect data or transmit information. Finally, we have energy harvesting. Technologies like solar powered sensors can collect energy from their environment, reducing the reliance on batteries and extending device lifespan. So, these enablers are essential for creating efficient and sustainable energy. Connectivity is the backbone of our modern world, enabling us to instantly communicate, work remotely, and access information on the go. The connectivity has led to increased productivity, collaboration, and access to a service anytime, anywhere. We can now work from anywhere in the world, collaborate with colleagues across continents, and access a wealth of information at our fingertips. This is made possible by a range of technologies, including Wi-Fi, Bluetooth, and emerging technologies like 5G and satellite internet. Consider the power of 5G with its high speeds and low latency. It's transforming industries and enabling new applications, from augmented reality to autonomous vehicles. And satellite internet is bridging the digital divide, connecting remote areas that were previously underserved. Connectivity is not just about technology, it is about empowerment. Our smartphones are not just phones anywhere, and our watches do more than just tell a time. This is the power of convergence. This is the power of convergence. Convergence is the merging of multiple functionalities into a single device. Take the smartphone, for example. It's a communication device, a camera, an entertainment hub, and a productivity tool, all rolled into one. It's a prime it's a prime example of how convergence has revolutionized personal technology. Similarly, smartwatches have evolved beyond simple timekeeping. They now integrate fitness tracking, notifications, and even mobile payments, making them powerful extensions of our smartphones. The result of this convergence is increased convenience, efficiency, and seamless integration of functionalities in a single device. We can now access a wide range of services and information without having to carry multiple devices. Furthermore, the integration of AI and Internet of Things into converged devices is taking these concepts even further. AI algorithms can personalize our experience, while Internet of Things connectivity allows devices to interact with each other and the environment. Convergence is not just about combining features, it's about creating a more seamless and intuitive user experience. It's about empowering us to do more with less. Divergence, on the other hand, is an approach to integration design that promotes information appliances with specialized functionality rather than generalized one. Think of a dedicated medical devices for specific diagnostics or treatments. These devices are designed with a singular purpose in mind, ensuring accuracy and efficiency. Similarly, specialized industrial control systems are tailored for specific manufacturing processes, optimizing performance and reliability. Even in our homes, we see smart home devices and dedicated functions, lighting, lighting, security, climate control, even focusing on specific tasks. The benefits of divergence are clear. It leads to improved performance, efficiency, and user experience for specific tasks. By focusing on a single function, devices can be optimized for that purpose, resulting in better performance and a more intuitive user experience. Furthermore, divergence enhances security and reliability through dedicated functionality with a focused purpose. These devices are less vulnerable to security breaches and more reliable in their operation. So, divergence is not about replacing convergence, but rather complementing it. While convergence offers versatil, versatility and convenience, divergence provides specialization and optimization. Both approaches play a vital role in shaping our technological landscape. The emerging wave of digital ecosystems is about the larger wholes of pervasive and interrelated technologies that interactive mobile systems are increasingly becoming part of. Think of a smart home ecosystem with interconnected devices and services, lights, thermostats, security systems, entertainment devices, all working together seamlessly. Or consider a connected car ecosystem with integrated navigation, entertainment, and safety features, enhancing the driving experience. In healthcare, we see healthcare ecosystems with wearable devices, mobile apps, electronic health records, enabling personalized and proactive care. The benefits of these ecosystems are significant. They offer seamless integration of devices and services for an enhanced user experience. Imagine controlling your entire home with a single voice command, or receiving a personalized health insights based on data from multiple devices. Ecosystems also led to increased efficiency and productivity through interconnected systems. Data can be shared and analyzed across multiple devices and services, enabling automation and optimization. Finally, ecosystems provide data-driven insights and personalized experience. By analyzing by By analyzing data from various sources, ecosystems can provide personalized recommendations and insights, tailoring the experience to individual needs. Ecosystems are not just about connecting devices, like I mentioned, they are about creating a more seamless, efficient, and personalized experience. They are about building a future where technology works together to enhance our lives. So I will jump to slide 22. I mean, these are examples of ecosystems, and you can read them. They are self-explanatory. I think we covered some of them in previous lectures as well. So in slide 22, I want to talk about, or 23, I'm sorry. I will talk about, Internet of Things. What's in this thing? An Internet of Things device is a combination of several key components. First, we have physical object, the thing itself. This could be anything from a light bulb to a car engine, a sensor in a field, or wearable device. Next, we need controller, the brain of the device. This is typically a microcontroller or microprocessor that processes data and makes decisions. Then we have sensors, which gather data from the environment. They act as the eyes and ears of the device, collecting information about temperature, motion, and many other factors. Actuators are the muscles of the device, enabling it to interact with physical world. They can control motors, open and close valves, or perform other actions based on the data received. Finally, we have networks, specifically the internet, which provides communication backbone for the device. This allows the device to send and receive data, connecting it to other devices and systems. These components work together seamlessly. The thing is equipped with sensors to collect data, which is processed by controller. Based on this data, actuators takes actions, and communicator ensures that the device can send and receive information over the network. So this is another slide that explains what is in this thing, and I want to talk about related areas. And this is the last slide I'm gonna cover, but the rest you can see these are also examples. They are self-explanatory. I will skip them from this. You can read about them separately. I have uploaded the slides into Canvas. So talking about related areas or terminology. So I will start with. Oh, sorry. I'm sorry. I want to talk about slide 26. So I want to start with M2M or machine-to-machine communication. So machine-to-machine communication focuses on direct communication between devices without a human intervention. This is a fundamental aspect of Internet of Things, enabling automation and remote monitoring in various industries. Another related area is the Internet of Everything, a concept championed by Cisco Systems. This expands on the Internet of Things by including not just devices, but also people, processes, and data, creating a truly interconnected world. Now, for something a bit different, Skynet. For those unfamiliar, Skynet is a fictional artificial intelligent system from the Terminator franchise. It's it's a cautionary tale about the potential danger of unchecked AI and interconnected systems. While fictional, it prompts us to consider the ethical implications and potential risks associated with advanced technologies like Internet of Things and AI. While Skynet is a fictional extreme, it highlights the importance of responsible development and ethical considerations as we move towards a more connected future. Understanding these related areas help us grasp the broader context of Internet of Things and its potential impact. And this is where I want to stop. Like I said, the rest of these slides are in the form of, examples and self-explanatory content. And thank you for listening. This is the end of Internet of Things Architecture, Part 1 and Part 2. Thank you so much. And please take a look to the slides in Canvas. Also, please check your homeworks that I have posted recently. Thank you.